Hi guys, so you're welcome to this particular class. We are going to be discussing oxidation and reduction reactions. Oxidation and reduction reactions are simply called redox reactions. But what exactly are redox reactions? Now, redox reactions has to do with reactions that involves the loss of electrons, the gain of electrons, or the sharing of electrons. Either way, there must be a recipient of electrons that were lost by another recipient. So if I have these two species, A and B, and I have electrons being lost from A and they are received at B, then the point where I lost the electrons, we call this loss of electrons, I'll say oxidation has occurred here at A. On the flip side, because B received these electrons from A, I'll say that B has gained the electrons. So reduction occurred at B. For my definition, it simply means that oxidation is the loss of electrons, while B is the gain of electrons. When A undergoes oxidation, I say that A has been oxidized. When B undergo reduction, I say my B has been reduced. Because A underwent oxidation and became oxidized by losing electrons to B, this means that if there was no B, A would have undergone oxidation to become oxidized. So I'll say my B is the oxidizing agent. Y is the agent that was responsible for A to undergo oxidation. So I say my B is the oxidizing agent. Also, on the flip side, if I consider my A, I will see that B was able to undergo reduction to become reduced because of A that gave it electrons. So the agent necessary for B becoming reduced is A. So my A becomes the reducing agent. Now, if you understand all of this stuff, it makes sense to say that oxidation is just a loss of electrons, while reduction is simply a gain of electrons. Coming back to reducing agent and oxidizing agent, we've been able to see that the reducing agent gets oxidized, while the oxidizing agent gets reduced. An easier way for us to understand this concept of, or the definition of these terms, is an acronym which we call OIL RIG. The OIL stands for oxidation is loss, while the RIG stands for reduction is gain. What are they losing or gaining? Is simply electrons. So oxidation is loss. So if you just remember oil, you remember that oxidation is loss, while reduction is gain. Alright, so let us talk about the concept of oxidation numbers, or what we call oxidation states. Because in redox reactions, there's always movement of electrons. One is losing and the other one is gaining. It makes sense for us to track this movement so that we'll know what's actually happening in the compounds. So for example, if we consider an atom, we want to know how many electrons that particular atomic species will receive or lose in a reaction. So the term oxidation number or state was developed. So oxidation number tells us the number of the electrons which a particular atomic species is willing to lose or gain when it undergoes a chemical reaction. So how do we determine the oxidation number of an atom? There are several rules that we must know that determines the oxidation number of an atom. So the first of them is that if we have an atom standing alone, which is a standalone atom, for example, lithium, the oxidation number On of lithium is equal to 0. Now, it's not just restricted to lithium. Any atom that stands alone, name it hydrogen, oxygen, chlorine, all of these, provided they are standing alone by themselves, they have an oxidation number that is equal to 0. The second rule tells us that if we have a molecule or a compound, for example, the sum total of the individual constituents that make up that particular compound, when you add all of their oxidation numbers, their sum will be equal to 0. So imagine that you have LiO2, which is lithium oxide, for example. The sum total of their individual oxidation number for lithium and also for oxygen should be equal to 0. Another rule that we have to know when we want to decipher the oxidation number or the oxidation state of an atom, we have to understand that if an atom is found in the group 1 of the periodic table, then automatically, if you find that particular atom in a compound, then its oxidation number will be equal to +1. So if you find it in group 2, it will be equal to +2. So for example, if we consider sodium chloride, for example, this is a simple ionic compound. If I want to determine the oxidation state or the oxidation number of sodium in NaCl, because sodium is located in the group 1 in the periodic table, then automatically its oxidation number is going to be +1. If I consider another compound, say magnesium oxide, for example, magnesium is a group 2 element. So by definition, it's going to have an oxidation number that is equal to +2. Now, as I told you earlier, all of these are rules that you use to determine the oxidation number of an atom in a compound. Another rule to consider is the rule for hydrogen. So hydrogen in compound with non-metals, normally we assume the oxidation state of +1. If it is found with metals, it assumes an oxidation state that is equal to -1. So if I consider hydrogen in H2S, for example, since sulfur is a non-metal, then the oxidation state of hydrogen here will be +1. But let us consider hydrogen in a metallic compound, say sodium hydride, for example. Oxidation number of hydrogen, because it's in a metallic compound, we say is going to be -1, following this particular rule that we have here. Hydrogen standing with metals is always going to assume an oxidation number of -1. So there's also a rule for oxygen. For oxygen, in every compound that you have, you see oxygen. For example, let's say water as in H2O. Whenever you see oxygen, the oxidation number of oxygen in a compound is always going to be -2, unless it's in peroxides. it assume -1. So if I consider water, for example, I want to know the oxidation state of oxygen in water. I follow the rule, because since water is not a peroxide, I'll follow the rule for oxygen, which means that the oxidation number ON will be -2. Now for hydrogen, we know that hydrogen, when it's with non-metals, it always assumes +1. So, but we have 2 atoms of hydrogen here. So each of them is +1 +1. That will give us, just multiply these 2 times. The +1 will give us +2. If we bring down this -2 we have here, it will be -2. If you remember our law that told us that the summation of the individual oxidation number for atom in a compound must be equal to 0. So +2 - 2, this is equal to 0. This simply means that the oxidation number of the hydrogen here, +1 and -2, is true for this particular compound, water. If we consider hydrogen peroxide, for example, H2O2, you will see that following these rules for peroxide, oxygen is going to have an oxidation number of -1. Oxygen is a non-metal. If I consider the oxidation number for hydrogen, when hydrogen stands with non-metals, it always occupies an oxidation number of +1. So +1 - 1 will give us a net of 0, because we said that in a compound, the sum of the individual oxidation numbers of the element that make up that compound must be equal to 0. So it's true for hydrogen +1 and for oxygen -1. You see how all of these rules make sense in the end. So you don't need to cram all of these rules, rather you just need to understand them as we go on. So now let's consider the rule for halogens. The rules for the halogens: whenever you see an halogen in a compound, know that it's going to have an oxidation state or oxidation number of -1. So for fluorine, bromine, chlorine, iodine, astatine, all of these halogens, we have an oxidation number of -1 when seen in compounds. So for example, if I have HCl, for example, the summation of the oxidation number of hydrogen and that of the chlorine will be equal to 0, given by the second rule we followed initially. If I follow this rule for halogens that says that the halogens must have an oxidation number of -1 whenever you see them in compounds, hydrogen will always have an oxidation number of +1 when it is standing with non-metals, like this case chlorine. +1 - 1 will always give us 0. So this means that the rule is true. Another rule we want to consider right now is that if you consider, let's say, lithium ion, for example, you know that lithium ion is not equal to lithium, the metal. While this has an oxidation number of 0 as an atom that is standing alone, this one has an oxidation number that is equal to the charge, which is +1. So whenever you see a charged or an ion or a charged atom, say chlorine, for example, chlorine ion, this will be the oxidation number of chlorine ion will be equal to the charge on the ion, which is -1. For magnesium 2+, the oxidation number will be equal to +2. I hope you get the idea. So in a nutshell, the oxidation number for a charged ion or a charged atom will be equal to the number on its charge. But this is just for monoatomic ions. Let us consider polyatomic ions. So what happens when we have a polyatomic ion, for example, NO2 minus? This is what many people call some sort of radical. So if I have NO2 minus, what they are saying is that all of this has a charge of -1. How do I get the oxidation number? In this case, the oxidation number for a polyatomic ion is always equal to the number on its charge. So if I add the oxidation number on the nitrogen to the oxidation number on the oxygen, it must be equal to -1. So this simply means that to get the oxidation number of a polyatomic ion, its individual oxidation number must be equal to the one on the charge. So let us look at certain questions that will normally come out in examination conditions. This is with practice. As you do more and more practice, there is no point for you to cram all of these laws. The more you practice with practice questions, the more you bring in some of these laws in use to trash some of the questions that you have.